Hello, this is Fotios Logothetis from Toshiba Europe, and I will be explaining our neural height map approach for the binocular photometric stereo problem. This is a joint work with Ignas Budvytis and Roberto Cipolla. The photometric stereo method aims to reconstruct the surface of an object from multiple images taken from the same point of view with varied illumination. The binocular case adds a second camera, which allows for a much better reconstruction quality with no sacrifice of capture speed. Our method models point light near field illumination, and it is applicable to highly specular objects such as the porcelain squirrel, whose images contain cast shadows and self-reflections. As a brief overview of our method consists of three key steps. Firstly, single view photometric stereo is performed on the two views to obtain a pair of normal maps and surface normal estimates. Secondly, a neural height map is initialized to fit the average of these two surfaces estimates with normal and depth loss. Finally, the neural height map is refined through volumetric rendering by applying losses to rendered normals to match the single view PS normal estimates, as well as the rendered images. An additional contribution of our work is the introduction of Lucas ST, the first near-field binocular photometric stereo dataset. This consists of 7 objects of several materials captured under 15 varied lights from a 45mm stereo baseline setup. A pair of 8mm lenses are used to image the objects at 15 to 20 cm distance, making the near-field effects prominent, thus increasing the challenge of the dataset. There is very little relevant literature on binocular photometric stereo, with the most recent work being by Wang et al. Over 10 years ago. This, however, is a classical optimization method, and it's only applicable to lambertian objects under directional lighting. In contrast, single view photometric stereo has seen a lot of rapid development recently, with deep learning approaches such as our IJCV22 work and Ikehata CVPR23 work, achieving remarkably normal accuracy under global illumination effects such as shadows and self-reflections. However, the single view surface estimates are subpar, as they usually suffer from considerable bending and other deformations. Finally, the use of neural surfaces has revolutionized the multi-view stereo and multi-view photometric stereo and has achieved remarkable accuracy with the cost of high acquisition and training times. Our method achieves similar accuracy as state-of-the-art multi-view methods while retaining the fast capture and train times of single-view methods. I'll now be elaborating further into details of our method. We assume that the surface can be expressed as a continuous height map. Z is a function of x, y in the world coordinate system, which is chosen as the average between the two camera systems. We know that the term height map is used to disambiguate between the surface, which is defined on world coordinates, and the two depth maps at the two camera coordinate systems. The surface is encoded using the SIREN neural network, which provides continuous and differentiable analytic normals and allows for fast convergence as explored in the work by Guo et al. For the single view photometric stereo case. In addition, for each surface point, we also include a scalar albedo, which is used for grayscale rendering. We know that we avoid to render RGB images in order to minimize synthetic to real gap. Rendering of the surface is performed with volumetric sampling with opacity proportional to the exponential of the inverse square difference between surface height Zs and ray depth Zr. We know that this volumetric rendering is required to account for left-right occlusions as it computes correct visibility. Finally, volumetric tracing and sampling is also used to compute cast shadows, which are essential for accurate intensity rendering. These are computing as the soft mean of the sigmoid of the difference of ray depth Zh and surface height Zs. To further elaborate on intensity rendering, we assume that the image irradiance equation consists of a product of the following terms. Firstly, there is a point light attenuation factor A, which accounts for light propagating from a non-uniform point light source M with direction Sm and attenuation factor μm. This is a standard term in the near-field photometric stereo literature. Secondly, we account for variable point albedos ρ sampled from the height map, as well as soft shadow indicator variables S, which are computed with the volumetric sampling procedure described earlier. Finally, we assume that the surface has a general but uniform material BRDF B, which in generality is a function of the relative angles between normal, lighting, and viewing vectors. We represent this BRDF function with a small 3-layer MLP, which is jointly optimized with the surface. We evaluate our method on the following two datasets. Firstly, we use the first two views of the diligent multi-view, which is the standard benchmark of the field. In addition, we provide evaluation and comparison on our newly introduced LookSSD dataset. For both datasets, in order to get a fair evaluation metric, we first crop the ground truth meshes by keeping only points that are visible in at least one of the two camera views. Then, we compute the mesh Hausdorff distance from the cropped ground truth to the reconstructed mesh. We now give some training details. We use the 5x512 layer SIREN with around 1 million parameters. We use depth, normal and rendering losses, with the depth loss being used in stage 1 only and rendering loss being used in stage 2 only. For depth and normal loss targets, we use the single view photometric stereo estimates. We did run the training for 300 epochs, which took around 8 hours of GPU time. However, as it can be seen in the image on the right, most of the convergence is achieved on the first few tens of epochs. We now discuss our evaluation and comparison with competing approaches, firstly qualitatively on diligent multi-view. We see that our previous single view method achieves smooth looking geometry that does however suffer from systematic surface bending and thus inflating the overall error. The method of Guo et al., which we extend into work in the two-view setting, assumes lambertian surface reflection and thus produces severe surface deformation at the specular highlights of this metallic object. PS-NeRF achieves overall good geometry, but does however fail at the concavity of the legs of the cow, possibly due to poor handling of cast shadows. Finally, our method produces consistent quality throughout the object and achieves state-of-the-art results. Indeed, numerically we perform all single and two-view comparators on all objects while achieving marginally worse performance than PS-NeRF using all 20 views. Please refer to our paper for additional ablations of the different components of our method. Moving on to LookSSD dataset, we observe that although we still achieve the overall best performance, the margin between the competing approaches is much smaller. This is possibly because of significant difference between the two views due to the relatively smaller focal length and bigger visual disparity, making it hard for all of the two-view methods to improve over the single-view baseline. Indeed, we saw here our results on LookSSD. We observe that the two metallic objects, bell and cap, are relatively challenging to reconstruct under the 15 available lights, with the rest of the objects achieving good performance. We believe that our novel dataset will be useful into improving future research in photometric stereo. To sum up, we presented the first neural-based binocular photometric stereo algorithm along with the first near-field binocular photometric stereo dataset. Future work includes relaxing the fully calibrated illumination assumption, which is however specifically challenging under point light illumination as well as a small number of views.